Dear students, welcome to the fifth session of our chapter 1. Today, we will discuss about the close packed structures in solids. In solids, we know that the constituent particles are very closely packed and they have a minimum gap between them, or the minimum vacant spaces are there. And this type of packing of particles or the spheres is said to be close packing. Now we will discuss the close packing in 1 dimension, 2 dimension and 3 dimension. In 1 dimension, how the particles are arranged, we'll see. There's only one way of arranging the spheres in 1 dimensional close packed structure. That is, they have to be arranged in a row touching each other. And the diagram is here, how the arrangement is. It's like a continuous chain where the spheres or the particles are arranged touching each other, right? So it's a row. In this arrangement, each sphere is in contact with two of its neighbors. So if you take the middle one or this sphere, we can see that if you take this one, it is attached or it is in contact with one and the second one. That means two spheres will be in contact with this sphere. The number of nearest neighbors of a particle is called its coordination number. So here a word is there which was before in coordination chemistry, coordination number and all. It's entirely different from this one. And here what does it mean? The coordination number is the nearest neighbors of the particle. That number, how many number of atoms or the spheres are attached to each other, is said to be the coordination number. Now in this diagram we can understand that one sphere, if you are taking it, is attached to two. So in 1 dimensional close packed arrangement, the coordination number will be 2. The maximum number of nearest spheres is 2. So the coordination number becomes 2 here. Next we will talk about the close packing in 2 dimension. 2-dimensional close packing structure can be generated by placing or stacking the rows of the close packed spheres. This can be done in 2 different ways. First one is square close packing. It is named as square close packing or SCP. The second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first row. That means we will be having a sheet of first layer. Over that we are just placing the second row so that the first one sphere will be exactly above the other one. The spheres of the two rows are aligned horizontally as well as vertically. If we call the first row as A-type row, the second row being exactly the same. Because it is same, we can name it as A-type only. Similarly, we may place more rows to obtain AAA type arrangement. This is shown here in the diagram. You can see here the first 1-dimensional arrangement is here. Over this, the second row is arranged. So you can see here the one sphere is here. Above that, just above that, the other sphere is there. Same way, the second sphere, when you see just above the first one, the second one is here. So if it is the third row, it goes on in the same way, or the pattern is there. That means the horizontal and the vertical arrangement is here. So this is what AAA type arrangement. And here how we are naming it as square close packing is, if any one of the sphere you are taking, how many spheres are attached to one sphere. This sphere, if you are taking, you can see here the attachment is this one, this one, this one and this one. So total how many spheres are attached to this single sphere? It's 1, 2, 3 and 4. When you just make a straight line to them, you can see it's a square. Because of the square, formation, the sphere's square formation, it is named as square close packing. In this arrangement, each sphere is in contact with 4 more neighbors. Thus, the two-dimensional coordination number will be what? 4. Before in the one dimension we have seen that if one sphere we are taking, it will be linked or it will be attached with 2 more spheres. So the coordination number was 2, the nearest neighbors. Now here in this two-dimensional square close packing, we know that when you take the one sphere, it is attached with 4 more spheres. So because of that 4 spheres attached to one sphere, the coordination number becomes 4. Also, if the centers of these 4 immediate neighboring spheres are joined, a square is formed. Hence, this packing is named as square close packing in 2 dimension. And the same diagram we have seen here, this one. We can see here the first layer, second layer, third and fourth layers are there. Any one of the sphere. If you take this sphere, how many spheres will be attached? This one. 1, 2, 3 and 4. So when you join these spheres together, you will get a square. And because of that square, it is named as square close packing. Now let's see the second type of two-dimensional packing, that is hexagonal close packing or HCP. The second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of the first row. So if there's a slight change in the arrangement, there will be a one layer which is arranged attached to the other spheres, and when you place the second row, the depressions will be filled with the spheres. So like that the arrangement should be there. If the arrangement of the spheres in the first row is called A type, the one in the second row is said to be B. Why? Because it is different. When the third row is placed adjacent to the second in staggered manner, the spheres are aligned with those of the first layer. Hence, the third layer is said to be A type. If it goes for the fourth row, it will be of B type. So this arrangement is of which type? AB type. In this arrangement, there is less free space. The space between them is very less. And this packing is more efficient than the square close packing, because in square close packing, little more gap is there between the spheres. So this is HCP is more efficient. Now we can see the diagram. Here you can see the first layer A type. The second layer or second row, when you are arranging, it is the depressions, that is these two spheres are having a little gap here. In that gap the sphere should come. So when you arrange it in this manner, we are getting the second row. Third row, when it comes, it's the same how we did the first one, that is A type only it will come. So it forms a hexagonal close packing. Now each sphere is in contact with 6 of its neighbors, and the two-dimensional coordination number will be 6. The diagram is here. We can see one sphere. If you are taking, how many spheres are there which is attached to this single sphere? 1, 2, 3, 4, 5 and 6. And when you join the dots, you can see a hexagonal shape. And because of that hexagonal shape, the close packing is named as hexagonal close packing in 2 dimension. And we can see here the gap between the spheres are very less compared to the square close packing. And the shape of the gap is what? It's a triangular in shape. So these triangular in shape gaps are said to be voids, and these are of 2 types. In one row, the apex of the triangle are pointing upwards, and in the next layer it is pointing downwards. You can see here the first layer, the gap, apex pointing downward. This point, triangle. Now the second layer's gap when it comes, the apex is pointing upward. Next layer when you are going, this one you can see it's going down, apex. Again here it's going up. So there then two types of voids or shapes are two. Now let's talk about the close packing in 3 dimensions. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers, one above the other. Let's see the first one. 3-dimensional close packing forms 2-dimensional square close pack layers, and in that how we can explain the structure is while placing the second square close pack layer above the first one, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically. Let's see this diagram. Here we can see first layer is there where we are having the one-dimensional. Second one, when you are arranging the layers, it will be in the depressions of the first layer. Again the third one. So it's almost the hexagonal close packing. Then it is only the 2-dimensional. When it is coming 3-dimensional, over this again, that is the gap is there in between these 3 spheres. You are placing the other layer of the sphere. So it becomes what? 3-dimensional, projecting outward. That is how we are explaining the 3-dimensional structure. Now, similarly, we may place more layers one above the other. If the arrangement of the spheres in the first layer is said to be A-type, all the layers have the same arrangement, and we can say that this lattice has AAA type pattern. The lattice thus generated is the simple cubic lattice, and its unit cell is the primitive cubic unit cell. This one we have seen. If we are having a NaCl structure, we have here number of cubes. The same structure you are getting a cube you are forming. So this is how we can explain the 3-dimensional structure when it is of AAA type. All the layers are in the same manner. Horizontally and vertically you can see the layers. So this is 3-dimensional one form. Next one, 3-dimensional close packing from 2-dimensional hexagonal close pack layers. Hexagonal close packing, that is HCP, how it is formed? The first layer is formed utilizing the maximum space, thus wasting minimum space. In every second row, the particles occupy the depressions, that is we name it as voids between the particles of the first row, giving AB arrangement. This we have seen in the first case. This structure has hexagonal symmetry and is known as hexagonal close packing. This packing is more efficient and leaves a small space which is unoccupied by spheres. In HCP arrangement, the coordination number is 12 and only 26% space is free. A single unit has 4 atoms, and you can see the pattern how it is forming. A type of the layer is there, and the second layer comes in the depression. So here again A is there, then B form, then A. So here you can see if you take one of the atom, it will be attached to 12 more atoms. So the coordination number becomes 12. Cubic close packing when you are saying, again, if we start with hexagonal layer of spheres and the second layer of sphere is arranged by placing the spheres over the voids of the first layer, half of these holes can be filled by these spheres, and the third layer are arranged to cover the octahedral holes. Following the pattern A, B, C, 3 different layers will be there. This arrangement has a cubic symmetry and is known as cubic close packed arrangement or FCC arrangement. And here you can see the first layer A, then B comes between the void. Again this arrangement is there for the C type, and then again A comes. So it is repeated again and again. Now let's talk about the voids or holes. The empty space between the closed packed spheres are said to be voids or holes, and it is of three types. The first one is octahedral void, tetrahedral void, and trigonal void. The first one we'll talk about the octahedral void. This void is surrounded by six spheres and formed by the combination of two triangular voids of the first and the second layer. This is how the octahedral void you can understand how it will be. So the three spheres are here in the downward apex form, and then three spheres are there in the upward form. So there forms a octahedral void. That is, you can see here 1, 2, 3, 4, 5, 6 points are there forming a hexagon, and it forms a octahedral void. This is how the octahedral shape it is having. We have seen that 1, 2, 3, 4, 5, and 6 points here in this void. And when you are arranging the three-dimensional structure, it is having a octahedral shape. So this is said to be octahedral void. The next one is tetrahedral void. These voids are surrounded by four spheres which lie at the vertexes of a regular tetrahedron. So the diagram, when we are explaining for the void, three spheres will be there attached to each other. The fourth will be in the depression, but the other side will be open. So you will get what the tetrahedral void. It's not having any gap there. If the fourth sphere is not there, then we can name it as trigonal void. This is how the explanation is there for the trigonal void. The void enclosed by three spheres in contact is called a trigonal void. Now you can see here 1, 2, 3, and backside one more point is there, which makes it a tetrahedral shape. Now coming to the trigonal void, here you can see the three spheres are there in connection with each other, and there forms a trigonal void. So this is how the three different voids we can explain. Thank you. We'll continue in the next class.